Hello and welcome to Advent of Code, day 16. Again, we are trying to solve both puzzles using Kotlin. And yeah, let's just start, I guess. Day 16, Packet Decoder. As you leave the cave and reach open waters, you receive a transmission from the elves back on the ship. The transmission was sent using the buoyancy interchange transmission system, BITS. A method of packing numeric expressions into binary sequence. Your submarine's computer saved the transmission in hexadecimal. The first step of decoding the message is to convert the hexadecimal representation into binary. Each character of hexadecimal corresponds to 4 bits of binary data. Yeah, okay, that looks fairly standard. The bits transmission contains a single packet at its outermost layer, which itself contains many other packets. The hexadecimal representation of this packet might encode a few extra 0 bits at the end. These are not part of the transmission and should be ignored. Every packet begins with a standard header. The first 3 bits encode the packet version, and the next 3 bits encode the packet type ID. These 2 values are numbers. All numbers encoded in any packet are represented as binary with the most significant bit first. For example, a version encoded as the binary sequence 100 represents the number 4. Packets with type ID 4 represent a literal value. Literal value packets encode a single binary number. To do this, the binary number is padded with leading zeros until its length is a multiple of 4 bits. And then it is broken into groups of 4 bits. Each group is prefixed with a 1 bit, except the last group, which is prefixed with a 0 bit. These groups of 5 bits immediately follow the packet header. For example, the hexadecimal string D2FE28 becomes this binary string, or binary number. Below each bit is a label indicating its purpose. The 3 bits labeled V are the packet version 6. The 3 bits labeled T are the packet type ID 4, which means the packet is a literal value. The 5 bits labeled A start with a 1, not the last group, keep reading, and contain the first 4 bits of the number 0, 1, 1, 1. The 5 bits labeled B start with a 1. And contain 4 bits of the number 1110. The 5 bits labeled C start with a 0. So this is the last group, end of packet, and contain the last 4 bits of the number. The 3 unlabeled 0 bits at the end are extra due to the hexadecimal representation and should be ignored. Okay. So this packet represents a literal value with binary representation 011111010, which is 2021 in decimal. Every other type of packet, any packet with a type ID other than 4, represent an operator that performs some calculation on one or more subpackets contained within. Right now, the specific operations aren't important. Focus on parsing the hierarchy of subpackets. An operator packet contains 1 or more packets. To indicate which subsequent binary data represents its subpackets, an operator packet can use one of two modes indicated by the bit immediately after the packet header. This is called the length type ID. If it is 0, then the next 15 bits are the number that represents the total length in bits of the subpackets contained by this packet. If the length type ID is 1, then the next 11 bits are a number that represents the number of subpackets immediately contained by this packet. That's a lot. Finally, after the length type ID bit and the 15-bit or 11-bit field, the subpackets appear. For example, here is an operator packet, hexadecimal string yada yada, with length type ID 0, contains two subpackets. Okay, I think I will skip over this now just to not read all of that, and we will look closer at this once we actually need to pass this. After okay, as in another example, here's an operator packet with length type ID 1 that contains 3 subpackets. Because this bit, this number of bits say 3, so we need to read 3 packets. After reading 3 complete subpackets, the number of subpackets indicated in 3 is reached, and so parsing of this packet stops. For now, parse the hierarchy of the packets throughout the transmission and add up all of the version numbers. Here are a few more examples of hexadecimal encoded transmissions. Alright, decode the structure of your hexadecimal encoded bits transmission. What do you get if you add the version numbers in all packets? Alright, this is a long one. So, a bunch of steps we need to do. And the good news is, at least right now, it doesn't look like it's a hard problem. It's just a lot of stuff to do and to do right. And the good thing is we have a pretty nice spec actually, and we just need to code down following this spec, and then everything will be awesome. The interesting thing to start with is, how do we read this data and how do we want to make it available to the next code that parses those packets? So we have, looks like we have kind of a two-step code to write. Like step 1 reads in hexadecimal stuff like this, makes somehow available to the next component a way to read bits. So second component will be some kind of parser, I guess. And the parser wants from the first component things like, give me 3 bits. And then we will look at those 3 bits, okay. And then we say, give us 3 more bits. Okay, and then we will say, give us maybe 1 bit, and then give us 4 bits, and then we will see, okay, it's a 1. We will need another one. Give us 1 bit and 4 bits, and then another one. Give us 0 bits and 4 bits, and then we have we know we need to stop, and then we put those bits together turn them into decimal, and we have a literal packet. And then we do this and we implement the next and the next, and then we at some point can pass all of them, and then we can write tests for all the sub pieces, pass this packet, and then we pass the whole blob here, and eventually we pass the whole puzzle input. Right now we only need the version numbers, which means we do not need to understand the numbers. At least we do not need, if we have a literal, like the first one here, we need the, what did it say? The version number. Like we need to pass this version. This is the wrong example. We need to pass the version, and we kind of need to pass the packet type, because that will help us understand what the other stuff is. And then for the literal, we kind of do not need to actually create a decimal. We only need to find the last bit group so that we can jump over them. And similar, I guess, for those operators, we kind of need to know when does this operator stop. We do not need to pass all of it, but at the end we are almost there. If we can pass a structure, then passing the inside is, I think, not that hard. It depends on what part 2 wants to do with them, because it says operators, so we might need to process them further in maybe a third step, because it performs some form of calculation. So I guess we will, in this part, we implement part 1, pass the input, make it, provide some nice methods to read parts of it. Part 2 is reading those parts and parsing it into packets, which in, I guess, part 2 of the puzzle we will turn into pass the whole packet, like all the data inside the packet. And then maybe there will be a part 3 where we need to use those packets and do something with it. Anyhow, let's start at the beginning. So we get a hexadecimal input like this. And then at the end, what we want is a bunch of bits. What makes this a super awkward protocol that we have things like 3 bits, 5 bits, dynamic length bits. Because otherwise, let's say we would pass this into bytes, which are 8-bit, and then we would read 8-bit things from it. That would be nice, easy, awesome. 3 bits. I'm not even sure if we have this, say, reader component where we throw in the string and I say 3 bits. What do I actually expect to get returned? There's no data type that is exactly 3 bits. So what do we want? Do we want... Actually, yeah, there are 2 ways to represent this data. Like, one is it could just return a string, 110, or it's an int of the value 6 in this case. Using a string is maybe weird because we got one character and blow it up into a string of 4, which makes, like in memory, this kind of data will become huge, but we can do this one step at a time, so maybe it's fine. It will also be huge if this is an int. We definitely need numbers at some point. I mean, there are kind of trade-offs. If we would like actually implement a system that does this, like if this would be something we want to do in production, then I guess we would want to process very small data types as the stream of characters come in. We don't want to blow them up and make them bigger. Like if you turn one character into 4, that doesn't seem useful. Like this could be a byte as well. The thing is, this will be like a very central piece. That might be hard to change along the way, so we need to make a good decision now. I guess the reader at the end wants numbers. But the problem is we need to take something like 3 bits and doing this, let's say if we pass those into numbers of, I don't know, in the worst case 32 bits, and then we need to bit shift all the time to take chunks out of them, and once this number ends we need to take the next one and maybe use chunks of both and combine them and return them. This is so awkward. In a production version we might do this because it's super performant probably, but here I feel like we will turn this into a string or a list of, or a stream of ones and zeros as characters, and then when we want 3 bits we take 3 characters and then we can pass those 3 characters into a number and then continue processing it. It's not the best way to do it, but it will be more straightforward to implement for this example, I think. So let's try that. Day 16. Let's create a file. We will have a part 1 and have a part 2. I feel fairly confident that we can solve this. It only feels like it will take a lot of time to finish this. Let's see. Maybe I need to do some cuts actually, because I don't feel like uploading like a 5-hour video. But let's see. What do we need? Maybe, so in the other puzzles we always started with read file, read from string, and then we know how we want to represent this data. But maybe in this one we only build small pieces of the things we need and then build the whole thing together from them. Like at a low level, we start at a low level, turning this into a stream of those 0 and 1s. And then we have build a second one that takes 3 of those and gives us a number like this. And then at some point, once we have all the tools we will build a parser. So maybe we actually need some kind of low-level test. But I do not even know what I'm going to write. But let's say I'm not even sure how to name this. Let's start with foo. Like, this is an input. And I guess what we expect is something that gives us like a stream of those things. And we do not want to turn the whole thing into zeros and ones. We could map it as basically, but that would mean we blow up this string into a huge thing for almost no reason. So maybe we need something that gives us a sequence of characters. Those characters are essentially ones or zeros. And then we do it on demand. This would be the idea. Yeah, let's try the sequence of characters. And we call this bit sequence. And what do we need to do? We need to just loop over our string. So input for as characters, and then to string. No, not sorry. For each, and for each character we need to now turn it into hex, into the bits. Either we pass this as hexadecimal and then spit it out as binary. That is one option. The downside is we create an int and then turn it back into a character or a string and then a character. Instead, what we could do is just build this map once. While x2 bits is a map of those things essentially. Okay, now I will again try to get the cursor at this multi-line. This time multi-line. Did I mistype multi-line? What the hell? I'm so sure there was a way to... Ah, here it is. Okay, this will simplify things a lot. And this will be a list of this, comma. This will be faster than parsing it into, will be faster than parsing this into a list of ints, or parsing it into an int and then parsing it back into character, which is, yeah, awkward. The only thing I'm wondering is there a way to get a sequence of characters? This is an int stream. Char. Oh, it's a char array. But maybe a char array is actually cheap. It's calling Javas to char array. Well, it doesn't matter at the end. So for every character we look up the hex to bits for this character. And I guess this can be null. Throw with state exception. Can't convert character. And then for every bit, we yield this bit. Let's take this and turn it into a sequence we can test. Test building sequence. How did we name this? Bit sequence. We want a bit sequence of that. And we assert if we take everything from the sequence and let's say we turn it into a list, and it's a list of characters, right? Now we join it to a string. Then this should be this string. Let's see if this works. It does not. We expected. Oh, first of all, we did it the wrong way. And we want to just join them without any separator, and now it passes. Okay, so we have something where we can throw in this and get an endless sequence, not endless, but a sequence of bits. What do we do with that? I feel like I want something like a scanner, like in a parser where we have a scanner that gives us tokens. And in this case, we will tell it something like give us 3 bits. And to do this, we throw in an input. And then, I guess internally, we will keep track of the sequence, bit sequence of this input. And then we want something like give us 3 bits, but as an int. I guess because we need numbers here. I wonder if ints is maybe too heavy. But for now, I do not really care much. We can still add other helpers if we want to. We could say next int and then something like bits, how many bits we want. And that gives us something like return sequence. And then we take this number of bits. And now we need to pass this because it's actually a sequence of characters, so we need to do the joining again. And now we need to pass this int, not int. Oh, that is the Java version. I guess there's something to int, right? Yeah, and this is binary, so something like this. Test scanning for next int. This is our sequence. And we say, no, this time we need a scanner. This is our scanner. And we say scanner, next int, 3 bits, and we hope we get a 6. Nice. Let's continue scanning. We say, give us 3 bits again. Oh, no, here, scanner, next in 3. And this should give us a 4. And it gave us a 6. Why is that? Gave us a 6 again. Let's test this with the test reading from sequence. Let's test this here first. If we take 3, then we expect those. And if we take 3 again, we expect 100. This is the case. That is not even the case because we didn't do what we wanted to do. We need to join them as string. Okay. The problem is I did not understand sequences correctly. Maybe. We expected 100, but we got 110 again. Does take not... It should... What? Like if we take all of them, then this is actually this order. But if we call take 3 and take 3, it is not. Returns a sequence containing the first n elements. Okay, it returns a new sequence. It doesn't move. It doesn't actually update this sequence. Why not? Why can I not? Like, so I need some. Do I need to keep track of the? Is the sequence then maybe the wrong thing? I was expecting a sequence to keep track of our position, and if I say take 3, I get 3 from the sequence, and I can continue taking from the sequence, but that is not what it does. Now I'm curious if I implement a for each element in this. Okay, we can't really look into this the iterator. So maybe I actually want to take an iterator. Can I take from an iterator? Oh, sorry. Next. I guess I could wrap this again into something that actually implements what I just wanted to implement. And that is sequence reader. Okay. And this means we pass in a sequence of characters. I don't need a generic one. And then I want something like take. And take does the following. We only keep an iterator. This doesn't need the input, and instead we have a reader, and we need a sequence reader now of this bit sequence. Okay, it's getting a bit involved, but I still think that is okay. So what we expect here is a list of characters. I wish there would be a way to say, give us the next 3. Before we implement this, let's take a look at the sequence again. Is there something smarter than what I'm doing right now? Yeah, all of them return a new sequence. None of them actually lets us iterate over the sequence, which means, or partially iterate, which means, yeah, we want an iterator. The problem is we cannot take multiple things, so we might need something like characters is a mutable list of char, and then we return, or we repeat n times just at iterator next return characters. Maybe that will be helpful, maybe not. Okay, let's oh yeah, in our test we still have our sequence, but now we test our sequence reader instead. Sequence reader. And now we take stuff from the reader. Test sequence reader. This is working. And now this one should work too. Awesome. There was one ugly thing here, and those are those ending zeros. Where did they come from? The 3 unlabeled 0 bits at the end are extra due to the hexadecimal representation and should be ignored. Okay. So this means not every literal will end with that. I hope, right? That is important information now. Will every packet need to be squished into a hexadecimal string, or will they overlap? And if there are more packages, those bits will be taken up by the following ones. How do we know this? The first is to convert into binary. Each character of a hex corresponds to 4 bits of binary data. The thing as itself contains many other bits of this packet. This packet might encode few extra 0 bits. Okay, the bits transmit contains a single packet at its outermost layer. Okay, but this doesn't have any. There's nothing that. Just a list of packets, right? The single packet is a list of packets, isn't it? Or not? No. I guess since those operators contain other packets, we might always have one. Either it's only a literal, or it's an operator with other operators or literals in it. Is this correct? A subpacket. Let's take another look at this. There's an operator with length 1. There's the length, which indicates that the length of an 11-bit number. Okay, this is only a number representing the number of subpackets. A literal value, a literal value, a literal value, but it doesn't have to be, right? This is a literal value because we pass the subpacket into a literal value, right? Okay, this is an operator packet which contains an operator packet which contains an operator packet which contains a literal value. Since an operator packet has the same as the previous, is an operator packet that contains an okay, so it's always one packet at the root which might contain subpackets. Okay, so this means the zeros at the end are for the last or for the first packet, so we only pass one packet. And I guess then the extra 0 bits do not matter because our parser will just pass one packet. And if there's more in our scanner, we won't read it anyway, so I guess we are good. We could try implementing a parser for this thing now. Let's try that. So we want a parser, and this parser will have a scanner, and this parser can do read, or let's say parse packet. Now the question, what do we return? Probably just a packet. I mean, we could solve part 1 much easier by not having to represent them as anything at all. We just go over this data, collect the versions, and then have the answer. But in part 2, I absolutely guess we will have to parse the whole packet anyway, so we might need to keep track of it. So maybe in part 2 we will actually build some nice interpreter, like we have a scanner, parser, and then interpreter that interprets this. That would be fun. And a lot of work again. I was scrolling to the top because I wanted to define those types somewhere. Maybe we do it here. So we will have maybe an interface of packets. Packet. A sealed interface. And a packet can be maybe it's even sealed class, because every packet seems to have a type. Well, we might not need to keep track of the type, since the type is will be an actual type in the language, programming language. But it will need a version, and this is also what we need at the end here, right? So let's say every packet has a version. And now there is a literal packet, right? Literal value. Literal value packet. And this is a packet. And it will contain the version. I'm not even sure how we can do this with the data class. Needs to have a I guess a literal will have a value. Yeah, it will just have a value. Value int. Oh, that is not possible. And if we turn this into an int, maybe yeah, we can turn it into an interface. Okay, let's try this. Sealed interface, and should have a version, so this can be a val now, and it's been override as well, and we do not need to pass it along. So something like this. We might change this along the way, but this means we can return a packet from here. And for now, we only care about parsing literals. Let's be test driven and write a test. Test parsing literal value packet. So this is our input. We need a parser, which is a parser that gets a scanner with this input. Now we say parser, please parse a packet. Then we say this is a literal value packet and 2021, right? Yeah. And the value of the packet is 2021. Why is this not available? Oh, because literal value packet. This doesn't. Kotlin will not know that we already checked this here. Okay, no problem. So this is our test. It's failing. And now we are implementing it, and then it should pass. And then we have step 1. We can pass the first type of packet. We need to pass the next one. And then we can either decide we keep track of the versions and the result along the way, or we build something that goes down like this tree of packets and finds all the versions and adds them. Okay. When we want to pass a packet, we start at the beginning. We say, give us 3 bits. If this is something else, this is oh no, packet version is scanner next int of 3 bits. Then we need to type packet type. Then we say when the packet type is 4, maybe we keep track of it inside the companion object. Type something like this. So we can say if this is a packet, literal value packet type, then, and this will call a function that parses the thing for us, parse literal value packet. We return a literal value packet. It's a to-do for now. So we parse this packet and we pass in the version because we already had to pass this. Other way around, version int. And if this is something else, then we throw unknown packet type. Now it says we can move this in, I guess, yeah. Which, actually I like how we wrote this, but if Kotlin prefers to move it in, which I think makes it harder to read, then okay. Then we return it. Could be private, yeah, okay. If we now run this, it still fails because there's still to do. The only thing we see is we are one step deeper in our stack trace. Okay. Now we read 1 bit, which is our initial loop bit, I guess. Loop bit equals scanner next int of 1. Oh, we actually could say next boolean. I like that. Which is return next int, or return when next int 1 or reader take 1 and then when this is 1 you return true. Return if it's 2 sorry, oh god, if it's 0 it's false, and else throw legal state bit is neither 0 nor 1. Now we do not have the value, but we can keep this. We expect never to hit this case. Take 1 still returns a list, but we can change this. 1 take is returning just a char, means return iterator next. This is the nicer to write. And then we can say where is the thing? Where's our scanner? Here, loop bit. We say next boolean. Now we need to somehow, so there will at least be 1, so we can read 1 already. This means where do we store those? We need to store those somewhere in a list. Do we need to read numbers more often? That we might want to add this to the scanner maybe. So this one, not in this stepped way, right? This will be interesting too, where we need to read a certain length. We probably need to add some kind of way to add this to the scanner to keep track of how much we read, so that we can stop. But that is for another day. We will create a list. Chunks, mutable list of ints, and then we have a scanner that we can already read the first 4, because there will always be 1. And if this loop bit is 1, so true in our case, then we continue. While loop bit while we loop, we say loop bit equals scanner next boolean, and then we say chunks add, and we read 4 again, and this should give us all the chunks. Now one more thing we need to do is combine the chunks together into number again. Now it's almost annoying that it's an int now, because if it was a string we could scan them together. Wait a sec, we do not need to have to read them. Next bits as string. We can just read a string if we want to. Now it's getting really powerful that we have this little character stream. We can say take those bits, join them to a string, and that is what we want to return. And then we can use this here actually. Next bits as string. We read those and then turn them into an int, and here we keep them around. So next bits as string. Now we have a string. Wow, that is nice. And then we turn this into a value. Chunks. And join to string. And then we say to int. Oh, join to string. And then we say return a literal packet value with the version and the value. And now can we pass this? Awesome. 1 hour in, we are able to pass literal value packets. Now we need to pass the other stuff, which are operators. We have operators with how operator structured. Just the literal value. Any packet with a type ID other than 4 is an operator. Okay. So for now, we will just have a type operator. Operator packet will be a packet. Now we do not need to keep track of the type because the spec says everything that is not 4 is an operator, so we will accept that. But I guess we will still need to keep track of the type. So this will get a type. Why is it complaining? Oh yeah, it still needs a version. Type. And then it has subpackets. It doesn't specify what this is, so we need packets, which is a list of packet. So this will be our operator packet. So maybe there will be a plus operator, which contains either numbers or more operators. Like a nice parse tree, essentially, that we read out of this super weird protocol. So we are kind of building a parse tree out of something super weird, is my guess. Okay, so the version we are already parsing. Now we need the type. So our else, well, let's start with the test. It will now fail. Parsing operator, and there are 2 types. One has the total length in bits of subpackets. So we need to keep track of how many bits we have read, and then we know if the subpackets have ended. This might be more complicated because we need somehow ask the scanner how many did we read, and then we keep track, and then okay, we have read enough and now we can stop. Or this thing which has a number that says how many subpackets there are, which is much easier to read. But at the end, both will be in the same data type, I guess. So I would love to start with the fixed version since it's easier, but for that we need to read the length, which is length type ID, which is only 1 bit. That will be easy. So we say with, let's say with fixed length, and the other one will be with bit length. This is the number of bits, so we start with this one then. And then we say, for now, this is an operator packet. Unknown packet type 3. Yeah, that is at least correct so far. Should we already add the other assertions even though they do not get? Yeah. So we need to cast this operator packet equals packet as operator packet, and then well, 3 is the operator packet type, and then the length, I think the number of packets, the size was 3 as well, right? Yeah. And then third true operator packet packets all of them are packet is literal value packet, like the children are all literals. Name shadowed. For this test we can just use it, and then we should also look at the values 1, 2, 3. How can we do this nicely? Maybe, well, 1, 2, 3 is operator packet packets map it as packet literal value packet, and then we map it value, and then we assert equals 1 is 1, 2, 3. Okay, awesome. Now we have the whole test case for this packet. Now we just need to parse it. So let's say private parse operator packet turns an it's a function, yeah. Turns an operator packet to do, and in the else case we always parse an operator packet, and suddenly we do not need the packet type. Well, we do. The operator is definitely interested in its type. And now we need to look at the length type, which is just 1 bit. So type length type is scanner read, oh no, next. We could read it as a boolean, I guess. Because it's either 1 or 0. Is this correct? There cannot be any other. Yeah. If it's a 1, it is this is the bit one, and this is the subpackets. Okay. So if this is false, which means 0, we pass a bit sized operator packet. If it's true, we pass a fixed size operator packet. Let's create those functions. There's still a to do. If it's a fixed sized one. Why keep I forgetting the fun keyword? There's no fun. It's a to do. Awesome. If we now run this test, we should go down the road of a fixed site length one. Okay, now we just need to read the length with this, which is always an 11-bit number. Well, packets, or no, number of packets will be scanner next int 11 bits. I really love our scanner, I have to say, especially once we added reading strings and booleans from it. That is really nice for getting through those values, because we can always pick the one that is just nice to process here, and we do not care about performance or squeezing this into a little code, little fast code. We don't need this. Still needs to be good enough for processing this, and I guess we take care of that at least. And now we just read the number of packets, and since the example is literals, this should just work. Packets, mutable list of packet, and then we say repeat number of packet times packets at parse packet, and we return fixed an operator packet with a version we haven't kept track of. I guess we need to pass this in here. Where's the version? Help packet version. No problem, we pass this in. And then need this here. Version, and here we need the version as well. Now we pass it along, yada yada. And here now we should have all the things. We have a version, we have a type, and we have a list of packets. That was so nice to write. Now I only hope the test passes. It does. That was easy. Thanks to the power of our scanner and the parser we are reusing. That was nice. Now I expect this to not be that hard. Okay, now the dynamically sized one. What do we need to read? The bit 15 bits, and this is the number of bits. Okay. Number of bits is scanner next int 15 bits. Correct? Correct. Let's actually write the test first. I was too excited. Which is test parsing operator with dynamic length. And this one. Parser equals parser of that, of a scanner of that, and then we read a packet. It's actually almost steal this. This time, well, it's still an operator. The type will still be no, wait, this here. Type will be 6. How many packets are in there? 2. Right? 2. And it will be 10 and 20. And they will both be literals, and it will be 10 and 20. I like that. That was quick to write as well. Okay, we didn't implement this. Let's see. Test. Test is failing. I'm mostly confused that it's... Yeah, why the beep is this actually parsing? Did I pass in the wrong thing? Yeah. That was still the dynamic packet. Okay, so this should fail. The parser should fail. Yeah, not implement. And this is here. Yeah. Okay. Now we need to keep track of how many bytes we read, because bits read is 0. Now we need to essentially, while bits read is smaller than number of bits, we read packages. Let's do the same as we do here. Say packets at parse packet, and here we return an operator packet with the things we did not pass in yet, a version and a type. Now we have version, a type, and packets. The only thing missing here is bits read is scanner bits read, and we also need to know since when. So we need something like bits so far, bits read until now, scanner bits read, and then we say bits read, and we are adding scanner bits read plus a minus bits read until now. Only those, and now we'll need to look at the scanner. This is one mechanism we can use. The other mechanism we could use is having a marker. Like on the scanner we could say mark, and then at some point we say, okay, how many bits did we read since we marked? Might be nicer to look at. Well, let's implement this. Well, before I do this, we need this essentially on the reader. The end of the day, because the reader is doing the reading. And what I'm interested in is if we have a mark here and bits since marked, bits read since marked. And can the iterator tell us where it is? Does it have an index or anything like that? Or do we really need to keep track of this ourselves? I don't want that. But it seems like we need to, which is okay. Index, we start at 0, or let's call it red. And if we take n, and we say actually let's call take here, because I have only one thing that changes the iterator, and then we can say mark. When we call mark, we set mark to red, and if we need the bits read since marked, we need to return red minus mark. We almost want a test for that, unfortunately. We're over here, test, fun, test. This is the reader. Reader marking. And then we take 3, and then we say reader mark, and then we read 3 more, and then we expect reader bits read and marked to be 3, and then if we read 5, we expect it to be 8. And so on. And then if I mark again and read 2, should be 2. Is that what it does? I think we have a compile error somewhere. Yeah. Version type, and this is no different. We will do scanner mark, then scanner bits read since marked. Oh, stop. No, it's correct. Scanner mark. Because now we need to mark it before we read the packets, and then we say while scanner bits read since marked smaller than this, continue reading packets. And then on a scanner we just need to pass this along essentially. Mark, we'll do reader mark, and bits since marked will return reader. Bits read since marked. Is this now? Yeah. And now we first need to test our marking functions. Starting to speak German. And I almost think we can now pass this, right? This was this everything? Okay. 63. What? No. Type 6, yeah, this is correct. Let's run this. Mistyped the wow, worked. Just worked. Now we can just add some tests for other stuff. Is this a valid name? Yeah. Yeah, nice. This should be an operator packet version 4. 4. Yeah, I'm really. Packet version. And I'm mixing things up. Maybe I should take a break. Which contains an operator packet. So this is an operator as well. Outer, out. Level 1 packet. Packet as operator packet. And this should contain 1 packet. How is this doing so far? Which contains an operator packet, which contains a literal value. Literal, right? Which contains an operator, which contains an operator. It needs to contain another one. We have a version 4 operator with a version 1 operator with a version 5 operator. Maybe just implement this thing now. Which will just traverse some versions. And when now we need to look at the type. When this is literal value packet. Well, yeah. Yeah. Then it is just the version. If it's a packet, operator packet, it is version plus packet sum of packet subpacket word, no, not version, some versions. let's see, this should be 16 packet, some versions. Some versions of, now we create small test cases of this, and to parse this, and we say equals 12. Sum. Now we need this for 23 and 31. Oh, here, let's start here. Then here, 23, 31. Let's run all the tests. And then we have our tools for part 1. No! So this one, did we copy this correctly? This one actually fails parsing. Why is this the case? Next boolean, take. We take something. Not ready? What does this mean, not ready? Next not ready? Does not have next. Does not have a next. Let's done. Okay, this one actually reads all the stuff and is not done. A different length type ID. Okay, what has the same as the previous example? Represents an operator packet version 3, which contains 2 subpackets. Each subpacket is an operator packet that contains 2 literal values. This packet has a version sum of 12. 12 we are able to parse. It's so weird. Only this one. It's a bit-sized one. Okay, let's run only this one. Then let's see. Bits to read is number of bits. And then bits read. Scanner bits read since marked. Let's see if we can see something weird. If we look at the reads, we need to read 84, and then we have read 0. Ooh, I see the problem. We have a nested one, and our marking only works on one level. If the next one marks, we suddenly lose track. Do we want to implement multi-level marking? I don't think we want, so we will just do what we initially wanted to do. Have a bits read function, bits read, and then the thing needs to take care of its own thing. Or we return its own marker. which is getting a little bit complicated for no reason, but I like this idea too. So the mark will just be in the marker. Marker, and the marker will be returned with red, and this one will actually move onto the marker bits red. Oh, and it needs access to the read. Private var reader sequence reader, or a function. I don't want to make this public otherwise. Well, red. What? So we pass in a function that returns the red count, and then we pass in red. Looks weird. So we remember this value and have a function that will always return us the current value. Now we go back to this, and now we create a mark, and then we say mark bits red. So we only track them for this instance of marking. And now we need to fix our marker test. Well, first mark, mark, and then we create another one somewhere here. Second, reader mark. Okay, now it gets a little bit weird to keep track, but we will do it. First mark will be 8. Second mark will be 0 so far. Now we copy this. Then we read 2 more. Then this one will be 10 and this one will be 2. Let's see. Okay, the nesting was tricky. I'm happy that this was covered by a test case. Okay, everything is green. Now let's implement part 1. Our puzzle input. Did we already save this at all? Let's this in here. No. Move this in. And this is day 16. This is the first time we do not have a read method. So maybe we'll not even write one. File of day 16. Read the text, trim it, and let's go. Need a parser. And then we pass a packet from it. We throw in the scanner, and then sum of versions is exciting. Come on. No, what is happening? Number format. Okay. Okay, this is a tricky one. This is longer than what we keep track of. Okay, we need to change our strategy here. Literals can actually be long. Which says here we need to say too long. See if this is good enough. All right, 957. That was a nice one. Is this correct though? That's the right answer. Let's take a peek at part 2. Now that you have the structure of your transmission decoded, you can calculate the value of the expression it represents. Nice. Literal values type ID 4 represent a single number as described above. The remaining type IDs are more interesting. We have sum packets that sum the values. We have product packets, the value is multiplying together. Minimum packets, the value is the minimum of the values of the subpackets. Oh, this is so nice. Maximum packets, the value is the maximum of values of the subpackets. Packets with type 5 are greater than packets. The value is 1 if the value of the is greater, arrow is 0. Type 6 less than, type 7 equal to. Okay. And we have some awesome test cases. So we need something to evaluate this, essentially. So kind of interpreter. The only thing before we start this is I'm wondering, are we okay with having just one operator packet and using the type to differentiate them? Or do we want to go all over and create types for all the different ones? I think since the evaluation is so easy, okay, we just need to evaluate. Since the evaluation is so easy, we will not have different types. We can just go by the type and be literally done. But we will do something cool and create a class for it. It's our interpreter. The interpreter needs a parser. No, it doesn't need a parser. We could say evaluate packet. And this will at the end of the day return an int. Now we go by when packet is literal value packet, we return its value. When it is an operator packet, we will have a function that it's operator. And still return an int. Now we go by type. When packet type 0 to do sum. If it's 1, to do product. It's 2, minimum. 3, maximum. It's 4, greater than. If it's 5 less than, if it's 6 equal to. Toot to do. And now we write some tests. Yay! Eval of that, or evaluate. Okay, we need parser with a scanner that takes an input. By the way, should we write a helper for this? And then we need an interpreter. And then we say, what is the result? 3. Interpreter evaluate this packet. Now we do this for a lot of them. It's the first one. Yeah, now we do this for this one, which should be 54. Then we do this for this one, which should evaluate to 7. Then we do this for this one, should evaluate to 9. This one 15 produces 1, or we need to make sure we use the right thing. And then this one produces 0. And then this one, oh shit, I copied into the wrong thing. Confusion, is this even right? Yeah. This should, which one? 9C should produce 0 as well. And one more. This long one should produce 1. Doesn't have operator preference, interestingly, right? No, the preference, yeah, it's usually coded in the tree during parsing, but there is nothing, no rule for us to actually do this. And then we have an else case here, throw illegal state exception, unknown operator packet type. Now we run this and we should have a lot of here we run all our tests and we should have a lot of red if we at any point get this to run. So this should return along this 2 because the literals are longs. Now we need to hope that longs are also long enough for whatever operations we do. Okay, let's start. Let's look at only the failing ones. I didn't take note of what they do, but let's see. If we have how many failing ones? 8. Let's implement sum. What is sum? It is the, we need the packets. Packet sum of evaluate it. We have 8 failing. And it doesn't even compile. A return expression is required. Yeah, that is actually true. Run this. 7 failing. So we made one parse. Product. Packets. Is there a product of? What's if you have a bunch of numbers? What's the easiest way to create a list of products? Why can I not think of anything? Do I really have to implement a product function? Okay. We have a list of longs and we want the product of all of them, right? Multiplying them together. So this means it's 1 and then for each product times equals it return product long. Okay, I did quiet int. Oh, this is probably a long now. And then we kind of need sum of as product of. What we need is product of how is this written here? Can just steal this. And then how did they call the parameter? Selector. We will call this a selector too, and then we turn this into a selector. And yeah, oh, T. Product of, evaluate this packet. Let's see, we have 7 failing and we have 6 failing. Okay, that worked. Minimum. Is it just the minimum? The value is the minimum of the values of the subpacket. Yeah. Evaluate it. And we can implement this one too. Max of. Nice. Only 4 failing. Greater than. The value is 1 if the value of the first subpacket is greater than the value of the second. Otherwise the value is none. Okay. Let's write this as first and second of the packets, and then if evaluate first is larger than evaluate second, and it's 1, else it's 0. Correct? The value is 1 if the value of the first is greater than the value of the sub. Otherwise the value is 0. These packets always have 2 subpackets. Less than, I guess is the same, is 1 if the value of the first is less. Copy. The value is less. Doesn't specify if they are equal, so they will go into the else case too. Let's run it. Still 4 failing. This one is not evaluating correctly. 5. Oh, oh, wow, what a trick. It is not 4, it is 5 and 6, and this one is 7. What the hell? If this wasn't on purpose, then yeah, okay, 2 left, and they both need equal to. Like, what the hell is operator 4? Equal to. Packets with the type are equal to packets, their value is 1 if the value of the first subpacket is equal to the value of the second subpacket, otherwise their value is 0. Easy peasy. It's this again, but this time with equals. Nice. Okay, and now I just want it to work on the first try. Here comes part 2. Come on, it will just work. It will be perfect. There will be no errors. The value will be correct. Execute part 2. Let's see, we read the file, we parse it, then we evaluate it. Let's go. Wow, that's a large number. It's a little bit scary. It's the right answer though. Awesome. I think that one was really fun because we had a nice spec that we just needed to go through and implement step by step, and then it worked. That was fun. Like the thing that has helped us a lot is the way we wrote a reader and a scanner, because we had this magical power of reading ints or reading strings or booleans from this input, because sometimes it was just easier to process them as a string and then later turn them into an int. Like when we needed to pass literals and we had all those chunks, we could decide, hey, we do not read them as int, we read them as strings now. Create a list of strings, put them, join them together, pass it as a bit string of bits, whatever it's called. And that was super nice and easy. If we would have turned this, instead of in a sequence of characters, we would have turned this into a sequence of ints that we need to bit shift and take pieces out. That would have been so painful. But it worked nicely. It is definitely not the most efficient way to implement it, but yeah, that was fun. Yeah, if you like this, leave a thumbs up, and yeah, I hope to see you tomorrow for day 17. I'm getting afraid. I guess it's getting harder and harder. So yeah, see you tomorrow. Bye bye.